This is part 4 of the preliminary lectures. In this part, we shall combine functions into new functions in the same way that many musical instruments combine to produce a symphony. Combining functions to make new functions. Now, in the beginning, the idea of a function as an operation or a machine was emphasized. Okay, so it's a machine that will transform some input into some output. Okay, now, so the idea here is that in this section we're going to study the idea of combining different machines to make a new machine. See, for example, a car is a combination of many machines that have been put together, and it now functions as a car. Okay, so now in mathematics, what happens here is that let's look at standard ways in which let's look at ways in which we can combine functions. Let's look at the standard ways. The first one is what is called the sum function. Okay, so think of, my old functions or my old machines are f and g. Now what I'm going to do is I'm going to combine this, and I'm going to call this the sum function. Now how do I define the sum function? Well, it operates on x, and what it does is the action of the sum function on x is just the sum of the old functions. Okay, so the operation of a sum function is the sum of the old functions f and g, right? So for example, let's give an example of this. Okay, so for example, let's say I take f of x. Let's make this as an example. So I take f of x to be x squared, and then my g of x to be x minus 1. Then the sum function f plus g of x is going to be the sum of the old functions, which is x squared plus x minus 1. Okay, so it's just the sum of what the two functions do, right? So now let's actually see how this thing looks graphically. So let's see the idea of a sum function graphically. Okay, so so in this case, here's the graph of the first function, f of x equals x squared. Let's put him in red, so he's this nice parabola. So here's our first function, f of x equals x squared. Then we've got the next function, which is g of x, x minus 1, which everyone knows is this function that, which is this line. Let's actually put it in blue. Okay, but it's not changing color. Okay, let's see if I can manage to change the color. Yes. Okay, so here is here's the function, my second machine or my function, g of x equals x minus 1. Okay, so it actually cuts at minus 1, right? So the idea here is that what is the sum function going to be? So in this particular case, the sum function is what it means, what this definition means, how we define the sum function. So remember, this is how we defined it. This is nothing but a definition. Okay, so this is how we define the sum function. So we create a new machine, or the third function, or the sum function, and what we do is that we take the action of f at each x, and we take the action of g at that very same x, and we sum them. Okay, so let's look at the action of my f of my old function x, f of x equals x squared at 0. So here the action is just 0. 0 gets transformed into 0 squared. Now the action of the blue function, which is my g function, at this point is going to be minus 1. Okay, so he's going to be minus 1. So in this case, I sum them together. So in fact, I end up just with minus 1. Okay, so let's just choose I'm going to put it in. So the sum of 0 and minus 1 is 1. Likewise, here at x equals 1, the sum here is going to be 0 plus 1. So therefore, it's going to be like that. So in other words, what we are doing here is that to find the graph of the sum function f plus g, what you must do is you must add the heights of, or add the heights of the graphs of f and g. Then you're done. So I simply add, so at any general x, you see, the height stands at g of x, see, and then here, this height is going to be f of x, and then I just sum the red height with the black height, and then I end up with, let's just see if the color works. I end up with a taller height, which is somewhere around here. So I do it at each and every x, and notice that I will get a kind of mellowed out parabola in this format. Okay, so therefore this is the function, the sum function turns out to be nothing but x squared plus x minus 1. Okay, so this is how this is what happens graphically. So similarly, we define the difference function. We will define the difference function f minus g, the difference function. So this is what is called the difference function, and what it does is it transforms x into the difference f of x and g of x, and so it's a difference of the two heights. Okay, then we look at the product function fg at x, and it just takes the action of f at x, g at x, and then takes their product. And then the quotient function at x, we define it as it takes the action of f at x, g at x, and then we then take a difference, right? So a special case of this multiplication function comes in when one of the functions is a constant function. So in this case, you just f is the constant function c, and then in this case, like kc or kc, remember that's the constant function. So so in other words, fg is just going to be c times g of x. So in this case, it's just going to be nothing but, so it's going to be okay, so let me be a bit more clear. Let's take the concrete case of f being the constant function c. Yeah. So now it maps all x's into c. Then this guy fg of x is going to be nothing but c times g of x. So in other words, this case, all it does, it just magnifies the g function by c, or the heights of the g functions. So if we take an example and I make c equal to a half, then the graph of a half of g is just going to be nothing but halving the heights of the graph of g. So in this case, let's say our g was this type of function. Okay, let's say this is our g of x. Then a half g of x, all we're going to do here is we're just going to halve all the heights. So I'm going to just halve all of them, and then I'll get a shorter. So this is called shorty, and then I get a shorty, and so this is then going to be a half g of x. Okay, right. So this is how this is one way in which we can combine two functions to get a third new function. And so notice that we are using what is called the arithmetic operations. Now, there's another operation which you can do on functions which which ties in with the idea of functions as machines or operators. And this is when we look at the idea of what is called a composite function. You see, and this is one of the great advantages of using a mapping diagram. And this is where you can clearly see what a composite function is. Okay, so let's start off with a concrete example. Let's say that I ask you to calculate, let's say we've got our function h of x is equal to 2x squared. Okay, now in this particular case, if I ask you to calculate h at, let's say, 3, what you would first of all do is that you would take 3 and then you would square him up first. Okay, then you will get 9. Then having got the 9, you will then, you see, you will then double him up. Okay, you will then double up the 9 to get 18. And this is how your mind operated, evaluated h at 3, which is equal to 2x squared. Okay, so so let's say, so in general, what is going on here is that notice that so one way of looking at this is that we've got two machines. So I feed 3 into the squaring function and out pops out 9, and then I then feed that straight into my second machine, which is the doubling machine, and then I get 18. And this is how I actually calculated h of x is equal to 2x squared. So, so what is really going on here is that let's call this function f, or let's call this function g, and then let's call this, okay, so let's actually just call, okay, let's call this guy f, and then let's call this function g, right? Then what is going on here is that, so our h of x, remember, which is equal to 2x squared, this guy is actually the chaining, or it is the composite of these two functions. So it is firstly going to be f done first, and then followed by g, okay, at x. So here you're going back to the Eastern culture of reading from right to left. So this guy acts first, the f acts first by squaring it up, and then lastly the g then follows up, then takes what f does. Okay, so so what's going on here is that this 2x squared, first of all, in order to calculate h at x, we first of all squared up the x to get x squared, and then we fed that guy then immediately into our g function, which is the doubling function. So f is my squaring function and g is my doubling function. And then remember, this is what I fed into my doubling function. So what does this function do? Whatever you feed it, it doubles up. Okay, that's what it means when you say g of x is equal to 2x. Whatever you feed it, it actually doubles it up, right? So in this case, you fed it x squared, so you double him up, and then you then get x squared. So this is the function h of x, which is equal to 2x squared, right? Now, we can actually show this. So with a mapping diagram, this becomes very, very obvious, okay? So remember, the domain of f you normally write as x, and our range of f you normally use the symbol y. So what we do here is that, notice that here I'm going to put in my x, so this is going to be my h, and this is going to be my y. So in this case, so here we have these two lines running parallel to each other. So I put my y-axis parallel to my to my x-axis. That's a mapping diagram. Now what I'm going to do is I'm going to introduce a third line here, and I'll call this my u-axis. Okay, let me see if I can just change the color a bit so So till, okay, I think green is going to be working. Okay, so yeah, it works. So let's look at our function, our u. So let's look at h of x equals 2x squared as in terms of chaining, in terms of chaining or composing or putting these two machines together, whatever way you want to say it, that makes you comfortable with. So let's actually look at h of x equals 2x squared. So let's look at it from the behavior at 0. So in order to calculate h at 0, you first square the 0 up. You see that? So therefore this is my f, you see? And then after you get that, whatever pops out, you then double him up. So if you double 0, which is my g function, you get 0. So that's why h of 0 actually is equal to naught. Okay, so let's look at 1. Okay, so the first thing here is that I first square up the 1. So notice that I'm squaring up the 1. So in this case, so f is my squaring function operation. So I square them up and I get 1. And then after that, I will then apply my doubling function, which is g. And then I will then double him up, and then I'll end up with 2. Okay? And then this is precisely, you see, and notice that this is precisely h. Okay? So this is h, so it's going to be equal to g of f. Okay? And then in general, if I have x, what I do here is that I square up x. Okay, let's change colors. So I will square x up, and then I apply my doubling function. So g doubles whatever you fed it. So in this case, my g will double up. What are you feeding g? X squared. So it doubles up x squared into 2x squared. And then this function up here is going to be my h. Okay. So right. So essentially, so what we're going to do here is that this is what is called a composite function. So we write it as f circle g. So this is my new function, f circle g. Okay. And so this is my composite function. This is what we call a composite function. See, it's before we had f plus g. So now instead of f plus, we have f circle g. Let me just erase this. And this, remember, it was actually g of f. And I compose, I make a third new function called the composite, g of f. And we define this as, you see, we start from right. So we first get f to act, and then whatever comes out, we feed it immediately into g. Okay? So this is the idea of, so this is the definition of a composite function. Right. Now, the first thing that we can see is that these two machines, f of g is not the same as g of f. Now, compare this. I mean, the sum function of f plus g is the same as g plus f, you see? But these two are not the same, okay? So let's give you a counter example, right? So all I have to do is I show you one x for which f of g, the operation transforms x into another number which is not the same as g of f's transformation. So let's say I deal with f of x, let's say it's x squared plus x, and g of x is equal to 3x plus 1, okay? So what I'm going to do here is that then I'm going to consider my pre-image of x equals 0, right? So now let's look at how does this composite functions f of g act on 0. Okay, so what it does here, so remember g acts first. So g, remember, is 3x plus 1. So g acts on my 0 to get 1. And then whatever g spits out is fed immediately into f. So what is f? F is x squared plus x. So in this case, it's just going to 1 squared plus 1. So that should give me 2. So this is f of g of 0. Okay. So therefore, I conclude that f of g at 0 is equal to 2. Okay. Now, let's consider g of f. So acting at 0. So here, f goes first. So who's my f function? Okay, so f is x squared plus x. So 0 squared plus 0, I still get naught. And then I must then apply my g, which is 3x plus 1, which is I triple and add 1, so I get 1. And so this is going to be equal to g of f. And so therefore, what I end up with g of f at 0 is going to be equal to 1. So notice that f of g transforms 0 into 2, but g of f transforms 0 into 1. So the two functions are not the same. Okay? Right. Now, with these composites, what we can do here is that there are two special types of composites that are used very, very frequently in first year maths. And this one involves what's known as the translation map. Okay, let me just get this thing back. Okay. So these are common composites. So let's see how we can chain and make new functions. Okay. So let's say I consider the translation map TC. So remember what this guy does. Okay, let's just get this thing off. Okay, so let's look at common composites. So in this case, let's consider this map TC at x, and what it does, it just translates x by c. So whatever you feed it, it just adds c onto it. So c could be 5. So for example, t5 at x is just nothing but x plus 5. Okay. Now, let's say we have some function that we know. Okay, let's say we've got a friendly function f. Okay, so this is a function we know his behavior intimately. So in this case, by now, you guys should be intimate with the function y equals x squared. You can draw the graph of it. It's symmetrical and it goes like that. Okay. And okay, so you know this guy, this is a familiar function at like the back of your head. I mean like the back of your hand. Now, let's actually make a new function, g of x. And what we're going to do here is that we're going to chain f with the translation function. Okay? So in this case, so remember, so this guy goes first. So whatever you feed x, it adds c onto it. So I get x plus c, and then you then feed it into f. Okay? Now let's switch the order. So in other words, I'm now going to switch the order into the translation of f at x. So remember, this guy goes first. So I first of all, f acts on x to get f of x. And then he goes last, which means that I must then add c onto it. So notice that the two functions, just by switching the order of the composition, is very, very different. Okay. So, so in this case, let's say I've got my friendly function, y is equal to f of x. Okay, this I know very, very well. Okay. So what I want to do is that from this graph, how do I graph the new function? Let's say I've got a new function, so I want to graph the new function y is equal to f of x. Okay, so let's just make c 2 for argument's sake. So I'm going to just make c be equal to 2. So how do I graph y is equal to f of x plus 2? Okay, so this is the translate f of t2, right? So then also, how do I also graph t2 of f, the reverse composition, which in this case is just going to be f of x plus 2. Okay, so that's the big question. So how do I graph these two functions? Well, the way I graph these two functions is different. Okay, so notice that here, this function, what I do here is that if I have something like y is f of x plus 2, what I do here is that if this guy is positive, you see, it's a positive quantity, I go counterintuitive and I actually shift him. I shift the well-known graph of y equals f of x 2 units to not the right, but to the left. Okay, so look at this. So if I have y equals f of x, so this is my friendly function, y equals f of x, then in order to get y equals f of x plus 2, what I then do here is that all I do here is that I take this guy and I shift him 2 units to the left. So notice that the nose of my y equals x squared is at 0. So if I shift him 2 units, the nose moves 2 units to the left. So it's going to be found at minus 2. Okay, and so then this is the graph of y equals f of x plus 2. Okay, so notice a horizontal shift to the left is going to graph f of x plus 2. So in general, if you have y equals f of x and you have y equals f of x plus c, what it means here is that you just shift y equals f of x c units to the left. Okay, right. So therefore, this one is a horizontal shift. Now, what about the other case where if we have y equals f of x plus c? If I have y equals f of x plus c, this is nothing but a vertical shift. So in this case, if I have, so remember this is y equals f of x. Now I've got y, how do I sketch the graph of y equals f of x plus 2? So notice that I'm just adding 2 onto each and every height. You see, this is x and then this is the height f of x. So if I just add 2, I just shift the whole graph up by 2. So therefore the nose at 0 lifts off 2 units up into the sky, and then I get y equals f of x plus 2. So there we have it. So that's the graph of this translate. Now, there is also the second type of composition function that is also very used frequently, is where we work with what is called the negation function. So remember, the negation function was given as f of n of x equals negative x. Just flips the sign around. Okay, so let's say that I've got my friendly function y equals f of x. So this is a function, it's well known and I'm very comfortable with. Okay, then if I compose f of n, in this case I will end up with f of, remember n goes first, so just negates the minus x. So in this case I get f of minus x, and so I get my new function g of x. Okay, so this is going to be f of minus x, right? So in this case, what happens here is that in this case, then I have another function, okay, h of x, and in this case, I just flip the 2. So I get n of f of x. So, so in this case, it's going to be the negation of f of x, right? So let's see how the graph actually works out to be. Suppose our friendly function y equals f of x has the following graph. Okay, so from -4 to 4, so the domain is from -4 to 4, and it looks something like this. Okay, now so now what we have to do is, so this is the graph of y equals f of x. Now what about the graph of g, which is equal to f of minus x? Okay, so in order to graph g, which is f of minus x, what we have to do here is simply reflect it across the y-axis. So look at the part of the function between 0 and 4. Think of this part as wet ink, and then just fold it along the y-axis and then imprint it, and what you end up with something like this. Okay, let me just do it in red. So this is the part from 0 to 4. So this is the part from 0 to 4. If you reflect this, okay, the red isn't kicking in. I don't know why. See, I don't know. Okay, I think it's now working. Okay, so what happens now is that when you reflect it across the y-axis, that part of the graph from 0 to 4 reflects as this. And likewise, the part from 0 to -4, it actually then reflects into across the y-axis as that. And so this is the graph of g of x, which is equal to f of minus x. So all you have to do is reflect across the y-axis. Okay. So let's give you a concrete case. Okay. So let's say our friendly function is equal to the square root of x function. Now, this function is only defined for positive numbers because you can only take the square root of positive numbers. Now, what about f of minus x, which is equal to the square root of negative x? Okay. So in this case, what happens here is that all we have to do is reflect. So we just have to reflect this across the y-axis, and then this is the graph of y equals square root of negative x. Okay, that's all you have to do. So notice that the domain will then shift. So notice that the domain of g turns out to be all the negative numbers, and the domain of f turns out to be all the positive numbers. Right. Okay. Now, what about the other case, h? Okay. So let's look at the case where we have h of x, and that is equal to negative f of x. Well, this one is very simple. Okay, so let's actually give a demonstration. So let's say I've got my function. Let's call it y equals x squared between -2 and 2. Then if you, that's my friendly function, which I know like the back of my hands. Then to sketch negative f of x, all you have to do is reflect across the x-axis. Okay, so I'll do that in blue if this thing allows me to change. Yes, it does. And so therefore this is how it's going to look like. So this is the graph of h, which is negative f of x. Okay, so it just reflects across the x-axis. Now, the third type of composition that occurs very frequently between a friendly function and an arithmetic function is when we compose it with a negation function. So here we have our friendly function, and then now we consider the function where we compose with the negation function. So this acts first, so it negates the x to negative x, and then the f comes in last, so you get f of negative x. And then we also have the negation of f of x, and in this case it is the negative of f of x, simply because f acts first and then the negation kicks in last. Okay, so in this case in this case, what happens here is that in this case, no, what am I doing now? Okay, the third type of function composition that happens between a friendly function and arithmetic function is the one where the arithmetic function is the multiplication function. So let's say we have our friendly function, then I compose my friendly function with my multiplication function. Okay, think of my c as 2. Yeah, then in this case this one acts first, so it multiplies c by x by c, and then f acts last, so it's get f of c of x. And then I let's say I flip the composition, so it's mc of f. Okay, so in this case when I do this, then I end up with what is called c times f of x, because f acts first, so I get f of x, and then I multiply out by c. Okay, so let's see how the graph of this looks like. Okay, so intuitively the graph of g, it actually looks like the graph of f, except it is c times as fast. Okay, so let's look at the graph of, okay, let's consider let's say this is minus 2 and 2, and let's say that the graph grows from minus 1 to 1, and this is the graph of my friendly function. So this is y equals f of x, and what happens here is that this is so this is y equals f of x, and notice that the domain is between minus 2 and 2. So now I want to sketch what about f of 2x. Yeah, what about the graph of g, which is equal to f of 2x? In this case, you see, this guy goes twice as fast. So rather than taking 2, you see, this is 2 units of time interval to grow from minus 1 to 0. It only needs 1. Okay, so in this case, it will grow from minus 1 to 0. Okay, let me see if it allows, if this thing allows me to change pen color. Okay, I think it will. Let's see, I think it will. No, it's not working. Okay, just wait. Okay, now it will. Okay, so this thing will actually allow me to change from minus 1. I mean, it will, so instead of going 2 time units in order to change, I only need 1. So in this case, I grow from minus 1 to 0 in half the time. Okay, so I only need 1 time unit of interval, and then to grow from 0 to 1, the original f of x took 2. You see, it took another 2 units. So here I actually only use 1. So it goes something like this, right? So it has exactly the same similar shape, but it actually takes twice as it does it twice as fast. Now, how do we actually calculate the domain of G? Okay, so we calculate the domain of G as follows. You see, look at this. This is being fed into f of x. Okay, so therefore my 2x has to belong to my domain of f. But my domain of f in this case is minus 2 and 2. So in this case, 2x must lie between minus 2 and 2. So this will then force x to lie between minus 1 and 1. So that's how you calculate the domain of G. Okay. So okay. So let's then look at the other case. Okay. So the other case now is what about the graph of 2f of x. So now we're going to look at h of x, so it's equal to double f of x. So in this case, let's change, and I'm going to try use the red button, the red pen. So we've actually already seen this case where all this thing is double the height of f of x. So notice that the domain of 2f of x is identical as f of x, except that the height gets doubled. So in this case, the height gets doubled to -2. And you see the height all gets doubled up to 2. So here height is 1, so I double him up to 2. So in this case, I end up with something like this. There. So notice the big difference that follows when you do it. Okay, right. Finally, okay. So finally, we now look at the idea of what is called even and odd functions, because these things happen very frequently in mathematics. Okay, so let's look at even and odd functions. Okay, so in an even function, what happens here is that an even function is when the function is actually immune to the argument being flipped, to the input being flipped. So f of x is identical to f of minus x. Now a prototype of this occurs in the form of f of x equals x squared. Because if I calculate f of minus x, I get minus x all squared, but the square of minus x all squared is just x squared, which is equal to f of x. So, so even powered functions are that. Now, what makes these even functions nice is that they are symmetric about the y-axis. So, in other words, if I know how a symmetric function and an even function looks like between 0 and 4, like here, then I only need, then I can know, I just have to reflect him across the y-axis, and then I know exactly how he behaves from -4 to 4. So using this symmetry about my y-axis, I can reduce my labor of graphing an even function by simply graphing between 0 and 4, and then just reflecting in order to cover the case from 0 to -4. Okay. For an odd function, in an odd function, what I then do here is that I work with f of minus x. An odd function can actually detect when you are actually giving in a negative input. So in this case, I end up with negative f of x. Okay. So a typical prototype of an odd function is odd powered functions like cubic functions like f of x cubed. So if I feed it minus x, I get minus x all cubed, which is minus 1 all cubed times x cubed. And so this is just minus x cubed, which is equal to negative f of x. Okay. Now, odd functions also have a symmetry where we only need to know how it behaves between 0 to 4, for example. So let's say my odd functions look like this. Then I know exactly how it will behave between 0 and -4, because they're symmetric about the origin. Now let me explain. What do I mean by symmetric around the origin? What it means is that I just simply draw a distance from the origin to that point. And all I do here is that I just reverse it through the origin, and I keep the distance exactly the same. So therefore, point 1 moves to point, that's his reflection through the origin, and I do the same to point 2, you see, like there's point 2. And then notice that all I have to do is there, and then that completes the curve. So this is what is called symmetry around the origin. Okay. So that brings us to the end of this lecture.